So not everybody wake up yet. Let's give another minute. So any questions for lecture yesterday? Everything is clear?
I have a question. No?
Sure, Edgar.
Okay. When you was explaining that we can get the dew point line and the bubble point line for a fixed temperature, but when I see the equations of the partial pressure and composition, and you mentioned that the partial pressure is the correspond to the pressure of vaporization of one component or the other. But when I see the equation, I see that I can just get one line, not two lines.
Yeah, that's the thing, because you shouldn't consider fixed pressure. So the idea is you need to find pressure where
fixed composition.
Yes. So for the given composition, you find temperature where your pressure is equal to bubble pressure. Actually, today we will have example where it will be a bit clearer. If you give me like half an hour, I will explain it a little bit better.
Perfect, perfect.
So we will show, I will show just one example how to do it when, let's say, instead of partial pressure, you're using K values. That is a bit more practical in the real applications. Okay. But the principle is exactly the same. Okay?
Okay.
Okay, good. Let's start. So we already passed 2 lectures, and I just decided to put a little bit of the summary of what we already learned. First thing we learned was first and second law of thermodynamics, and more or less I tried to derive all of the quantitative relation based on these laws and few other things. Then Gibbs phase rule, super important thing to understand thermodynamics in general, because it gives you understanding when you have combination of certain component present in certain phase, how many degrees of freedom you have. And based on that, you can draw the diagram. You can understand if your diagram is correct or not, and things like that. Single component phase diagram, we learn a little bit we learn a lot how to identify, interpret it, and also a little bit how to draw, how to create it. Then we look into qualitative description of phase diagram for binary mixtures. And this is just combination of 2 single component phase diagram, but because you now mixing things, you have extra degrees of freedom, and that change a little bit geometry of your phase diagram. And then we look into the very basic phase equilibrium relations, and so far it's only 2 quantitative equations we learn. We will see much more today. One is Antonin equation that will give you, for the single component, the transition pressure as a function of temperature. And this is correlation. So A, B, and C here are regressed for each component individually. And then Raoult's law that just explain how to combine this pressure in case of mixture. This is the simplest one. We will see today much more complicated relation, how to compute phase equilibrium and phase behavior in general. Is it clear, all the descriptions that we have before? Yeah, more or less? Because if it is, then there is quiz. And the question of number one is, which statement is right? So read, I can, audialize it. We have two-phase is a line in PT diagrams of pure component. Three-phase is a point in PT diagram of the binary mixture. Single phase is a line on a phase PT diagram of the pure component, and two-phase is a point. So which one is correct?
The first one, I think.
Why?
Well, the second one is not correct.
Okay, I agree, but
The other one, I think, also.
Let's try to count how many degrees of freedom is. So we're talking about PT diagram, and it's pure component. So we're talking about F is equal C minus two phase. That means 1 minus 2 plus 2. So that means you will have 3 degrees of freedom, right? No, sorry, 1 degree of freedom. 1 degree of freedom. And we already mentioned that 1 degrees of freedom, so 0 degrees of freedom is a point, and 1 degrees of freedom is a line. So indeed, the first is correct. But this is type of question that you right away look into the Gibbs phase rule and decide what is right and what is wrong. This is directly relevant to the Gibbs phase rule. We never look into the mixture with more than 2 components or more than 2 phases. Actually, 3 phases we look, but it's still possible to understand. So you have 4 components that can form up to 3 phases, and you fix pressure. How many degrees of freedom?
It's 4 minus 3 plus 2 is 3, right? So you have 3 degrees of freedom.
This is correct, except that it says that it can form up to 3 phases. That means it also can form 1 or 2 phases. So it's from 1 to 3. And this is the thing that usually you mixing, for example, hydrocarbon gases with water, hydrocarbon gases, liquids, and water. So I know that at most it can form 3 phases. That is vapor hydrocarbon phase, liquid hydrocarbon phase, and water, because water would never mixing. It's its own phase by its own. Yeah. So that means when I'm mixing these things, I can expect from 1 to 3 phases, all kind of combinations. So that's the idea, that while you mixing the components, and for components you may have like gas, liquid, and intermediate component plus water. So it will be 4 components that can form up to 3 phases, but you don't know if they form or not, these 3 phases. It depends on the proportions. It could be 1 phase. If, for example, you have a lot of water, then everything will dissolve in water. Or if you have a lot of gas, everything will vaporize in gas. So that's the idea, that until you do this multi-phase flash, something about phase behavior you don't know. Next question. Which statement about representation of two-phase condition on arbitrary diagram for the binary system is wrong? And two-phase, what it couldn't be. And there is point, line, surface, or volume.
I think it can never be a point.
It cannot be the volume. And the reason here is the following. So we're saying that there is binary system. So number of component 2. And you have two-phase condition, -2. And then that means that degrees of freedom could be from 0 because you can plot it at the fixed pressure and temperature, right? So we're saying arbitrary diagram. So the degrees of freedom, you can fix for your diagram pressure and temperature, and then this two-phase condition will be the point. If you fix only pressure, for example, it will be line. If you not fixing anything, it will be surface. And then but it couldn't be volume because you cannot have degrees of freedom more than 2. Okay?
But
yeah, our phase diagrams, we plot, remember, you can plot phase diagram as a plane in the 3D space for the binary system, but you also can plot it as not surface, volume in the. So there is all kind of possibilities to plot the diagram. I can say, I want to plot diagram for the fixed pressure, for the fixed pressure and temperature. It may not have sense, but yeah, I can. The thing is that if you have at maximum 2 degrees of freedom, that means you cannot go farther than surface in your diagram.
That's the logic.
Yeah.
Please tell us the limit.
Yeah, because limit in this case is given by the number of component and number of phase. That's it. Okay. Last question. Why Gibbs energy is used for phase equilibrium? Because it is potential function, because it's continuous at phase transition, because it's partial Molar property. All 3 statements are correct. What do you remember about Gibbs energy?
It has to be continuous at the phase transition, the Gibbs energy.
Yes. But actually, it's also potential function and Molar properties. So it's all 3. That advantage of the Gibbs energy, because it's potential function. That means so it could be uniquely represented by our degrees of freedom, and it's partial Molar properties. That means it's defined for the fixed PT and the rest of the components. So that's 3 advantages of the Gibbs energy. That's why we use it for phase equilibrium. Okay, for today we look into the compressibility factor. It's already a little bit familiar for you from our challenge course. Then I will touch a little bit in more details. Again, you're already familiar with the equation of state. I will just show you a few more things. We look into the phase stability test based on actually either due bubble point pressure or due bubble point temperature. It's more or less the same. And last is the multi-phase flash. And also we'll try to do one solution, practical solution in the class, if times allow. Now, so far we look mostly into ideal behavior, and I only touch a little bit what's happening when it's not ideal. What is the ideal solution? First of all, it means that molecules are not interact with each other and not having volume. That means more or less what's happening, all the properties is about communication, how molecules are represented in the space. So if you have gas, and it's ideal gas usually, the distance from the molecule is large, and more or less the pressure is small when the distance is large. When you start to moving them together, it has larger pressure, but they not occupy the volume. That means, yeah, however they communicating, they just flowing there and create this volume without occupying it. So here you can see what's happening if you compare your difference between PV over L. This is your pressure volume relations versus your pressure. And you can see that whenever you change the atmospheric pressure, your volume is not changing too much for not changing for ideal gas. And then if you look into the normal gases, like real gases, like H2, N2, CO2, you can see that they're deviating. So actually, by increasing the pressure, your volume will be affected. This is all happening at a fixed temperature. Or if you change the volume, pressure will be affected. So it's either way in this case. And this is the main difference between real gases and ideal gases, that there is interaction between the molecules, and by increment of the pressure, molecules may interact more, and that affect the volume. In the ideal gas, it's independent. Most of the time, if you look into the behavior of the real gases at low pressure, they're all quite close to the ideal gases. So if we're talking about something much lower than even atmospheric pressure, you may observe that the gases behave like close to the vacuum. The gases behave similarly. Now, the difference between ideal and real gases was quantitatively described first by van der Waals. Actually, he wasn't introduced the compressibility factor, but he introduced the equation of state for the real gases. And more or less the idea is that if you look into this difference in volume between ideal and real gases at certain conditions, that is what's called compressibility factor. So this is most common correction that introduced by van der Waals. He actually was for a long time professor in Leiden University. No, sorry, he got PhD in Leiden, but then he moved to Amsterdam and he was teaching there. So more or less, he suggested this equation of state that connects your volume of real gases with pressure and temperature. And here he introduced these two parameters, A and B. That is, one is attractive forces and another is repulsive forces. We will take a look a bit later on this. So the idea is that this volume is different, that you find from here, is different from volume that you having in ideal gas. This is the volume of the real gas. And then if you take ideal gas volume and real gas volume, you compute compressibility factor. Another person who make quite a bit of the impact on the compressibility factor, he actually introduced it by deriving it from statistical mechanics. It's Heike-Ons. Both van der Waals and Heike-Ons have Nobel Prize. Ons have it for super capacity or something. But one of the interesting story about Ons, that he was teaching in Delft for a couple of years, actually 1881, 1882. So at that time, Delft was polytechnical, it wasn't yet university, but yeah, so he was teaching maybe in the same classes we have now, of course not in our building. So more or less he derived this compressibility factor, Z factor, from statistical mechanics. And more or less what he said that you have this interaction between all kinds of molecules. And in the statistical mechanics, he looked into interaction between two molecules, then between three molecules. So two molecules is this, NB over V. Then for three molecules is this guy, etc., etc. So most of the time we're truncating it, but always remember that all of our equation of state, all of our computed Z, computed compressibility factor, it's only rely on the interaction between at most two molecules. But in reality, it's 3, 4, and infinite. It's just that these other interactions, they much weaker. So that's why you can kind of ignore them. That more or less corresponds to this viral coefficient B. By introducing this coefficient, he can explain several phenomena that before wasn't clear. For example, B is less than 0 at low temperature and equal to 0 at boil temperature. So that explains why our compressibility factor have this form when it's decreasing and then increasing again as a function of temperature. And then, yeah, C usually truncated. So this is a typical form of the compressibility factor as a function of pressure. And the main idea, we already discussed it, that the main idea is that at the low pressure, our actual volume is less than ideal volume. And this is because there is attraction forces between the molecules. So molecules are bringing closer to each other. And this is happening until you reach, so first, this volume will be decreasing comparing to ideal volume, but then molecules are close enough to each other and they start repulsing. And this is what starts happening here. At some point it reach pressure where volume of actual and ideal is the same, and then it will become higher because again, ideal ignores the volume of molecules. So when you push it, when you squeeze it, it's just reducing the volume. While in real case, you have these molecules that don't let you to reduce it due to the repulsive forces. Now, if you look into the equations that describe this behavior, this is what we call equation of state, and there is plenty of them. Depends on where you are in terms of chemistry, you can use a lot of them. But in general, there is two types that are cubic equation of state and everything else. And the idea of the cubic equation of state is more or less the following van der Waals equation of state. So all these equations, Redlich-Kwong, Sauer, Penn-Robinson, etc., it's some extension of the Penn-Robinson equation of state. And the main attractive thing is that it's cubic. That means you always have at most 3 solutions. While if you look into the more complex equation of state like SAFT, and there is CPI, there is a few other, it's not cubic. So there could be up to 27, I think, for SAFT equation of state, roots of the equation. And there is no guarantee that you find all of these solutions and pick the right one. So that's just general description. Now, if you look into the van der Waals equation of state, again, he derived it from statistical mechanics. And here you have, this is my repulsive term, and this is my attractive term. So the one help you to decrease the volume comparing to the ideal volume in the beginning, in the low pressure. And then the other don't let you decrease it more. And this is what's happening after you increase the pressure. So often called energy parameter, and B often called as a molecular co-volume or excluded volume. So once you introduce this equation of state, there are several ways of how to derive this A and B parameters. And we're talking right now about pure components. Yeah. So you just have one component and you want to see how molecules are behaving when you start increasing pressure, how the volume of this mixture is behaving. So there is usually 3 ways how to determine the parameters. And the first one is critical property expressions. They actually, most of them are at some point derived from statistical mechanics with some assumptions. And you can derive more accurate, because here, as I said, usually we're truncating this anything more than interaction between 2 molecules, you can include more interactions. So critical property, statistical mechanics, and in some cases, you can just directly regress it to your measurements. So if you have measurements of your vapor pressure and density, you can derive your own A and B for the given species, for the given chemical matter. Now, almost 100 years, so we're talking about, even more than 100 years later, one of the breakthrough was done when there was several, there was Redlich-Kwong equation of state, and then Sauer added this alpha function. But in general, this is equation of state that mostly used now in chemical engineering and petroleum engineering, and it called Sauer-Redlich-Kwong equation of state. So what they did, they introduced, if you compare it between these two, they introduced 2 things. They introduced this correction alpha function here. What's going on? This correction alpha function that represent, it actually was just correction to capture feed of the pressure, vapor pressure feed for C1 to C10. So this is done specifically for capturing the normal alkanes in the chemical engineering at that time. And in other corrections they introduce is this correction. If you look into the original van der Waals equation of state, it was v squared term, and now it's v squared plus some linear dependency. The same story here. So now instead of A, sometimes both of this A by multiplied by alpha called as an A operator. So be careful in the literature, but in original papers, they have just this correction. And then B operator, they can again define by critical property expression. Here is example of how they can be defined. They also introduce additional parameter, eccentric factor. So in addition to critical pressure, critical temperature, they introduce one extra parameter for each component that you need to know or measure. And then you have this A, B, and alpha computed out of these three parameters. Or it's the same story. You can take some new chemical species and regress saturated vapor pressure and liquid density, regress your parameters to this experimental results. Now, last but not least, around the same time, a little bit later, there was Penn-Robinson equation of state. They more or less inherit the same alpha correction, but they just introduce extra relation here for parameter B. And again, they derive A, B, and alpha from these critical properties. They're slightly different. So this is more or less what's happening in current, let's say, if you look into the petroleum engineering, classical petroleum engineering, Penn-Robinson equation of state used a lot. But for the modern energy applications, you need more and more complicated equation of states because in a lot of cases, we need to deal with the brine, and brine is a water with dissolved chemistry that wouldn't be predicted accurately using this Penn-Robinson equation of states. So there is some correction needed. One of the big questions, how you apply this equation of state for the mixture of the gases. And there is actually, you need to apply two rules, one called mixing rule and another combining rule. So if you know your concentrations of the component in phase, and equation of state is estimating your volume for the phase. So if you have, for example, three-phase mixture, you need to solve equation of state 3 times to estimate the Z factor or V for each of these 3 states. And here you can see that if you know X, that is concentration of component in phase, then, and you know your A for A alpha for each component and your B for each component, then you do this combining rules first. You create this matrix, and in this matrix on diagonal, you have just A alpha, because this is interaction between molecules with each other, the same molecule. And this represents the interaction of molecule of the species I with species J. So if you're mixing methane with decane, this is interaction between these molecules. And then you need additional parameters that called binary interaction parameter that simply describe this interaction between these two molecules. So once you construct this matrix, then you can just sum it over concentration of each species, compute A, compute B, and now you substitute it here in the equation of state and solve equation of state for the mixture. So it's a little bit more of bookkeeping, but quite straightforward. And this is a big advantage of the equation of state, that it's with some simple mixing rules, it can predict quite accurately the volume, the compressibility of your complex mixture in real life. Now, it's important to know that there is alternative mixing and combining rule that could be used, but most of the time we're using the simple geometric combining rule and ideal mixing rule. Now, more or less, this is how you can estimate the compressibility factor for your mixture. But in reality, what we want to know how it's flash, how it's split when you mix it. So if it can warm more than one phase, if it can warm two phases, three phases, and if it can form these phases, what is the separation between these phases? And this is what is done based on the flash calculation. I will show you simple flash calculation first, and then I will show you in a little bit more details how it's also done. And on practicals, you will see all of them and try to practice how to compute all of them. Now, I will also remind you about these important definitions because they use a lot in the flash calculation. So first thing is we have number of moles that most of the time when you do this flash calculation translated into the overall molar fraction. And overall molar fraction is just the number of moles of your component I divided by the total number of moles. Or you can think about this as a number of molecules divided by the full number, total number of molecules. Now, if I can form two-phase, and we only look into the two-phase, then these molecules will be split between liquid and vapor. So you're mixing your guys, you have vapor and liquid, but in vapor, you still have some of the heavy molecules that otherwise, if you wouldn't mix them, would be the liquid. But because you mix, some of them vaporize and participate in the vapor phase. And some of the gas molecules, very light molecules, will dissolve in the liquid. So that means that any number of the molecules will be separated between these two phases. For any components, even when component is very, very heavy, still few molecules will be flying in the vapor phase. That's the idea. And then it's just bookkeeping, because if you now sum of these molecules and sum left and right hand side divided by not total number of molecules, you will get molar fractions of each phase. L and V, it's molar fraction for liquid and vapor phase. And then if you do a little bit of the reshuffling, your total overall molar fraction, then you will find that overall molar fraction is equal to component phase fraction divided by fraction of the phase for the liquid and for the vapor. And in a lot of cases, that's called local mass balance. That means that whatever split in the two phase, it will preserve. Yeah. So if you're mixing this number or your component at this concentration, it will split between the liquid and vapor phase. it wouldn't disappear anyway. So now this is the main rules that we will use. And here is the question we want to answer. If I have certain composition and certain pressure, temperature is fixed, so it's both certain pressure and certain temperature. Now, would a mixture, this composition represents the mixture of two components, would it be form liquid, vapor, or two-phase? And to answer for that, you can use vapor-liquid equilibrium flash calculation. How it's working? For the simplest cases we start with, we will be using so-called partitioning coefficients, because in a lot of cases for the partitioning coefficients, you can derive them as either as a correlation as a function of pressure and temperature, or you can have it as a dependency. So anyway, for the given component, you can obtain this K that just represent what is the fraction of vapor and liquid concentration of the current components. And this is just the ratio between this vapor and liquid concentration. Let's say if you have very light component, then K value will be much bigger than 1, because most of the molecules will go to the vapor phase, and some of them might dissolve in the liquid phase. Now, if you have very heavy components, then K value will be much less than 1, because X will be larger. So this is the idea between these partitioning coefficients, and in a lot of cases, they can be represented for each component independently as a function of pressure and temperature. Now, if I take this equation and this relation, and in this equation, I just substitute instead of L, I just substituted 1 minus V, because sum of L and V equal to 1. Now, what you can do, you can rearrange a little bit. So instead of Y, I substitute just X умножить на K, substituted here, and I have only dependencies between Z and X. And then reshuffle it a little bit and write these equations. So here I just divided Z by this relation. And then because I know that Y is equal to K multiplied by X, I just multiply K here and get this relation. Is it clear? Maybe it's a little bit fast, but I think. Any questions? How I get this? So this is my relation. First substitute Y as a Kx instead of Y here, get this. Then rearrange, just take X out of the brackets. Get this guy, and now I just divided, so find X as a function of Z. So divided this relation by this guy, this bracket. Get this and find this. So the advantage of this reshuttling is that my K and Z are input. And that means if I know V, I will know X and Y. Yeah, because K is known, Z is my input. This is what I want to compute split. And the only unknown thing here is V. Okay?
V is the fraction of vapor, right?
Yeah, V is a fraction of vapor. Yeah, be careful with V as a volume and V as a fraction of vapor. I try to do volume a little bit different later, but Yeah, so V in this case is a fraction of volume phase. It was a little bit messy to rewrite everything on L, but maybe next time I should do this. Okay, so this is what kind of rearrangement I did. And now, if we return back to here, what I can do now, using these simple equations, I can compute when my composition become liquid, become a bubble point composition, or when my composition become dew point composition. That means here I have single phase composition where I have last bubble of gas. Here I have single phase composition. I mean, they formally two phase, but just on the border. When I have last drop of liquid. And the idea is that for the given composition of the, so composition is not changing in this point. The only changing thing is the pressure. And I know that at this pressure, my composition is the dew point composition. And at this pressure, it's liquid bubble point composition, right? So for any composition, I can find these 2 points. And then the idea is, if I have my current pressure, if I'm here, I will be in vapor. If I'm here, I will be in liquid. If I'm here, I will be in two phase. That's the main idea of these computations. Okay? Very silent. Everything is clear or not clear at all. So here I just did rearrangement. This is super simple. And now I want to use this rearranged relations to just, for the given composition, compute my dew point and bubble point pressure. I will show it before the break and then we can do something else. Okay, so the idea is I only have these two relations that now translated in these two relations. Now, how this relation will be look in the dew point composition? I forget. Okay, let's start with the bubble point composition. So first of all, in bubble point, I know that my Z is equal to X, right? So if I'm on the bubble point composition, I don't have any, so there is the last bubble of gas. That means this guy should be equal to Z. Or other words, this guy will be close to zero, will be exactly zero, right? Guys, wake up.
Yeah, but the denominator should be 1, right? Because of the plus 1.
Yes, there is no problem with the denominator if V equal to 0. So it's become 1 and X equal to Z. But one thing that you don't know is what's happening with Y, because Y is not equal to Z. Y actually will be equal to K multiplied by Z. Just if you substitute the same V equal to 0 here. And another thing that you know, so your Z originally, by definition, it should sum to 1. But then you have another relation. You know that Y should also sum to 1. Because by the definition of X and Y, if you're summing across them, across all the components, this concentration should be equal to 1. So what you do, you're combining these two relations, and this is a relation that satisfies the bubble point curve. It says that if I sum of all of my K multiplied by Z, it should be summed to 1, just from the definition we have here. So your Z become X, your Y become KZ, and then you also know that sum of Y equal to 1. That gives you this relation. And very similarly, you can do the same similar relation for dew point curve, because at the dew point, your V is equal to 1. That means if you just do rearrangement, you will find that, so Z equal to Y, X equal to Z over K, and you also know that sum of X equal to 1. And you have this relation. Is it clear? So more or less, it says that if I have K as a function of pressure, then I need to find the pressure that satisfies this relation. And then I need to find another pressure that satisfies this relation. And this will be my dew point and bubble point pressure. So now the question is how I can find this pressure. Any ideas? How I can solve this equation? I have some correlation for K as a function of P.
Oh, exactly.
What?
And I guess you have to find the roots for a correlation.
Yeah, so I mean, in general, this is nonlinear equations that you can solve using, let's say, bisection, right? Or Newton method, depends on how you know K as a function of P. But this is, so the idea is you need to find pressure that would satisfy this relation. And this is the main idea of finding bubble point and dew point pressure. Okay, guys, let's make a break. It seems a little bit too much maybe for the morning. We will take the break and then we try to solve this ourselves. Let's return back. So 9 is 9:40 at 9:55. And please download there is Python script in the Brightspace that we will use to just look how to solve this problem. Okay? Good. So 9:55. Yeah, so the idea here is that for the equation of state related computations, and here we only use correlation for K values, you need 3 types of parameters: critical temperature, critical pressure, and uncentric factor, this omega. So this is parameters, and this is a small database for each component from CO2, blah, 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 to C7. And then 3 types of parameters. So what this procedure gives you, it just return needed parameter for needed component. And then we use here it's so-called Wilson K-value correlation. I will show you a bit later today in the lecture. But more or less, it's correlate pressure as a function of, correlate K-value as a function of pressure, temperature for the given set of the components. Yeah, so if you know, if you, for example, you're saying my binary mixture between in this case, CO2 and C6, and then you pass it here, it will return K value, correlated K value for CO2 component and C6 component. Now, once you have this K value, you can compute our saturation pressure, either bubble point pressure or dew point pressure. And this is procedure that only missing bisection loop that you need to add. And more or less what this procedure do, you passing temperature, you passing composition, and the number of components. And then you defined if it's bubble point or dew point. So BP is true means it's bubble point, BP is false means dew point. And here, the only difference will be how you compute your residual function. It's either sum of z multiplied by k minus 1 or z divided by k minus 1. Just following our lecture here. Yeah, so one case is this residual function, another case is this residual function. And then what it does, it's starting from the large bound. I just take the bound between 1 bar to 800 bars. It's compute K value, and then it's compute residual for the left, residual for the right. Of course, they need to be different sign, because remember, bisection only works when you have monotone functions that crossing the zero. That means on the left, it should be one sign, let's say minus, on the right, it should be plus. So if they both either minus or plus, this is error. This is problem with the K values. That can happen, for example, if you're mixing two gases, if there is no liquid, then two-phase never would form. And then what you need to add here is just bisection loop that computing your pressure, either bubble or dew point, and you need to call it here. Yeah, so very simple task. We have 15 minutes, and I just opened the rooms, and I will help each of you to solve it. Okay? So guys, is it clear what to do?
Yes,
Yeah.
we just
First, we
get
need
to the
the
file.
file from Brightspace, I think.
Where could we find the file?
It's in lecture, if you go to lecture 3.
Content lecture 3.
Yeah, found it.
And it will be enough if one of you just writing it down. Okay, I'll check the other groups and then return back to you.
One of you has already has it or not?
Hi guys, how's it going?
We're just starting.
Yeah.
I'm looking for the code from the first quarter for the bisection method.
Yeah, but it's not super difficult, right?
Yeah.
So you just need to check if it's less than 0 or bigger than 0. And then it's either taking left or right.
Ah, okay.
And you can check it the same way as I did.
The object function.
What's
Hi, Dennis. Is it possible for us to screen share to each other?
Yes, it should be. No?
Ah, now it is somehow. Did you just activate it, or were we just fooling around?
No, I didn't do anything. I did this multiple participants some time ago.
Okay.
I wasn't able to share before, but okay, now I can. Should I share, guys?
Yeah,
or-
please.
Yes, Javier.
So I have the practical here. And this is the new one. So you just have to do the back section, right?
Yeah.
You have to define the two things. Just let me find how it's what's done here. Right. So the two boundaries. Or the
So you already have two boundaries on the upper. There is left and right. No, don't go too far.
oh, here, yeah.
Yeah,
left
so
and right.
you have
Okay.
left and right. And more or less what I did, I just multiply by left all the time to check the sign.
Right. Left.
So here you can see it. Check key values consistency.
Yeah. What would this be? The res? Oh, res is lambda z. Okay. Function. So we just go.
So first you need to compute pressure in the middle, right? So you can just.
Yes,
The average. So we can. Oh,
midpoint.
yeah. Or just go. Mid. Oh, it's going to take the two. Was it left or right?
Yeah.
All right. Perfect.
Now you need to compute key value in this point. Just can copy paste and replace. Because more or less there is pressure, you compute key value based on this pressure.
Mm-hmm.
So that is this way.
We just take this, but okay. Let's copy this way.
And then you pass, you need to pass it to residual. Just compute the residual.
What is the comp part in the K value, like the C or
Comp
MP?
is the number of components.
Oh yeah, of course. Yeah.
Ah, okay. So we're left. We just calculated, right?
Okay, I'll check the rest and see how.
And
Thank you.
the K, okay, perfect. The K will just be replaced with this new K, right?
Javier, I think you have an invitation.
I think we have also to define, because we have an R left boundary, but we don't have an R right boundary, right, in the script. There is, if you go in the saturation pressure function.
Yeah, I saw that, but I'm trying to, because bisection, I think you just, no, I don't know.
You need, yeah, you need the left and the right boundary, right?
Not necessarily. You can just take. So I'm using left to understand about the sign. And you
Okay.
can use exactly the same.
Okay.
I will show you just what I did. So you
Okay.
compute pressure in the middle,
Yeah.
then you estimate K value, you have residual, and now you only need left to decide if your pressure going to the left or pressure going to the right.
Yeah. And then
Okay.
yeah, exactly. So we can take so the midpoint is B1, let's say compared to practical 1, you have B1 plus B2 over 2. That's just left plus right over 2.
Yeah.
That's your midpoint. And then we make a decision whether or not to put whatever next value we get on the left or to the right.
Yeah. And don't forget to recompute K value for this new pressure, right? K value and then residual, and you're done.
Okay. So if I were to share my screen, I'm not allowed to.
You're not? I don't
No.
know what's happening. Try again.
No.
Again?
No.
Let me see if I can do it also from outside.
So midpoint would be left plus right, and then
Divided by 2.
yeah, and then
It's still not working, the share?
let me see. No.
Shoot.
And,
So
and
wait.
then you use the midpoint in the vapor liquid function. Okay.
Did you manage to do anything?
Yeah, I'm busy. So
Okay,
yeah.
and you cannot share the screen?
Yeah, I don't know if the others are here as well.
Ah, I see.
I'm
Okay.
trying to implement the bisection method, but I'm yeah, figuring it out.
Okay, yeah. I'll give another 5 minutes and then show, help a little bit.
Yeah.
Hi, Dennis. I have a question.
Sure.
Should we decide the sign by the REIs?
Yeah, maybe I shouldn't. I did it very. Let me show. Can you see my screen?
Yeah.
So what I did, I more or less use exactly the same rule as here. Yeah, so if you compute residual, so this is my middle point, this is my K value, this is my residual. Now, if residual multiplied by left is bigger than 0, that means they have the same sign. And I need to move it to the left, otherwise to the right. So you don't need really both left and right, guys.
Oh yeah, I thought I need to calculate R left and R right and decide by the product of these two. Yeah.
Yeah, you can do it either. This is a bit more compact. Yeah. So.
Okay. Thanks.
Yeah, I was trying to do the same.
Yeah. Thanks.
Okay. Okay, I'll check with the other groups.
We're a bit stuck, Dennis.
Okay. I will show you how I did it. Maybe that would help.
Mm-hmm.
Okay, so first of all, you don't need to keep pressure as in the loop, right? So it's iterations, so you don't need to keep previous iterations in a way.
Okay.
So what I do, you compute the middle, left, right. Then you don't need to remember to recompute key value and compute right residual. And then more or less, you use the same principle as here. You take left and multiply your new residual by left. If they bigger than 0, that means this multiplication, it means they have the same sign. And you need to move the left boundary to the pressure. Otherwise, you need to move the right boundary to the pressure.
I still see Toon's screen share and not.
Oh.
Yeah. Let me see. Maybe I should stop share.
Yeah, I think you should stop share.
Ah, yeah.
Okay.
I was already wondering.
You see it now?
Yeah, now I see it.
So I use exactly the same check. So I've got my middle pressure, evaluate K, evaluate residual. And now I multiply my new residual by R left. And if they have the same sign, that should be bigger than 0. If they have opposite sign, they should be less than 0. Right?
Yeah.
So that's the idea. And then you move left or right guy and check residual in there. That's it. Okay? In 2 minutes, we return back and I'll show it for everybody. Okay?
Yeah.
Oh, Dennis, I think we've finished the first part on bisection over here. Do you think it's all right like this? Oh, you're still on mute.
Dennis, you're still muted.
Sorry. You compute vapor liquid, but now after that, you need to recompute residual because you didn't recompute residual here. Take a look. I don't know if it will share it now. Can you see my screen or?
Oh, I can stop sharing first. Okay, I can see you.
Yeah.
Okay, good. So one thing, after you compute vapor liquid, you need to recompute residual with this K value because K value doesn't give you answer, residual gives.
Oh, yeah.
Yeah, so, and then you did it right, but with the wrong function. Indeed, you multiply R by R left and you compare. If it's bigger than 0, you're moving left guy. If it's less than 0, right guy, and check this. And then in the end, you just fill this PBI and PDI.
Yeah.
That's the idea. I will stop, more or less move everybody back and then explain it for everybody.
Okay.
But
great.
Except
Thank
this
you.
residual recomputation. Okay, welcome back. So the main idea, I just want to wake you up a little bit. So that's that. But of course, it's maybe a little bit too complicated to apply everything right now. You will have practice, not today, the next time, with few things, including this bisection solution. But the main idea is you have pressure as a half. You need to evaluate k-value, but k-value doesn't give you residual. Residual is actually this guy, yeah? So then you need to call residual, check if it has the same sign with the left, then you're moving left. If it has different sign, you're moving right, and then you break. And then you call this guy in the loop. And what last thing I did, because here I'm checking. So at some, if you start increasing your composition, at some point, you may have lose the k-value accurately estimated. No, sorry, it's not k-value. It's so in some cases, your k-value might not be estimated accurately. And in this case, I just break it earlier. But the idea is that then what you will observe, that will be your saturated point for your gas, saturated point for your liquid, and this is your envelope. So this is your bubble point, this is your dew point. So that's something you will practice later, but just to give you some understanding how it usually works, you already have everything to solve all of these problems in your arsenal. So you just need to remind yourself what means certain things.
Can you show the third cell again, just quickly?
Okay.
Sorry.
No worries. First cell, you mean?
The third cell, this one. So, okay, so you loop to get the points. Yeah, it makes sense. Thanks.
Yeah. So I just loop over these guys and compute for each of them. Yeah, you cannot do it in vector form, unfortunately, in this case. Okay, so let's continue then with the rest. So that was bubble point and dew point calculation. But now imagine that at this composition and this pressure, so you estimate bubble and dew point, and it says you in the two phase. So now what you need to do, you need to compute flash. You need to understand how this composition will split into the liquid and vapor. And this is equivalent to finding the tie line. You will find this is your y, and this is your x. This is how your composition will split at the given pressure and temperature. And this is the next step, and you can use exactly the same equations. It's just a little bit more in the terms of the bookkeeping. So this is your full system of equations. And by some reasons, instead of having sum of the x equal to 1 and sum of the y equal to 1, you need to have this equation. This is sum of the x minus sum of the y, and it should be equal to 0. So you have NC equations like that, NC equations like that. Yeah, I don't remember why I start again from L, but more or less you can just substitute your L directly here by V that I'm doing here. So this is your full system of equation. You do exactly the same trick. You find x as a function of z. So let me maybe show it a little bit in more details. So this substituted here. this substituted here. Now you do exactly the same trick as the previous case. Now you have just this guy depends on V. You rearrange and you have X and Y as a function of V when Z and K is input. And now what you do, you substitute this guy here and this guy here. And you've got single equation. Is it clear? So this step is exactly the same that we already did. Now the only difference is when you have two-phase, instead of looking into sum of I equal to 1 and sum of X equal to 1, you subtract one from another and you've got this guy equal to 0, 1 minus 1. And now you substitute X and Y into this equation. What you've got this equation. And what is the advantage of this equation? There is only one unknown. It's one equation, one unknown. Actually, it's independent from the number of components. In our case, it will be 2 components. Let's say I will pick K1 fixed, K1, K2. Your input is pressure and composition. Based on pressure, you evaluate K values. And this is my composition. And now what you need to solve this equation. We also call it a Rachford-Rice equation. This is one thing that proposed by these guys, Rachford-Rice. They have engineering degree award for it. So what you obtain one equation that you need to solve as a function of V. And if you have it, this solution, that means you will find given V, you return back, substitute V here, and you obtain X and Y. So this is my equation. This is monotone equation if it's in between these two asymptotes. And what I'm interested in solving, I'm solving it in the interval 0 to 1. So if you want to solve it in the interval 0 to 1 and it's monotone, you can use exactly the same trick. You can use bisection. So you're starting from 0 left, 1 right, and then you find the solution that is somewhere here. And this is what we call flash calculation. Is that clear? Good.
Yes.
There is a little bit of, so this step is exactly the same as we did before. The only thing is now substitute all of them into one equation and get one equation in the residual form. And once you have it, you can solve for this given K and Z. This is my solution. So V is around 0.6, let's say. And then you substitute and find X and Y. So suddenly you solve all of your problems. You know you're in the two-phase by stability analysis. And now you do flash in the two-phase and you get X, Y, and V. There is another possibility to use the same technique when you're outside of the two-phase. Let's imagine you fix this pressure and so this is my pressure, this is my composition. And what I can find extension of the tie line. So this is my tie line, and this is its extension. And by extension, I also know that if it's here, it will be liquid. If it's here, it will be vapor. This is called negative flash. And it's simply, so now I use exactly the same example, but I changed my composition. I have much more gas phase, gas component. And if I solve it now, I will find that my solution is here. So my V will be bigger than 1. Physically, it doesn't make sense, but mathematically, this is indication that you're in the single phase. And what is a single phase? Because V is bigger than 1, it means you're in the single phase gas. And this is just one abstraction when instead of trying to solve your flash in between 0 and 1, now I'm solving my flash in between these two asymptotes. Anybody can guess what are my asymptotes, how they defined? First of all, why there is asymptotes here? When it's happening?
I think it's because the denominator is close to 0, right?
Yeah, but I guess you know this, Shamil.
No, I don't know this actually.
So these two asymptotes corresponding to these two denominators equal to 0. So when this denominator equal to 0, you're dividing by 0, and it's not possible in math. So that's why you have these two asymptotes, and actually you just need to make V, so this denominator equated to 0, and you find where these asymptotes located in terms of V. So it will be somewhere in the place bigger than 1 and some of the values that is less than 0 usually. So that two asymptotes, and if you're solving your solution between these two asymptotes, you will find your negative flash that indicates if you're in the two phase or in the single phase. For in this case, you don't even need to run stability test. Your negative flash will give you right answer independently if you're in the single or the two phase. In two phase, that will be consistent answer. So you will have V between 0 and 1, and you also find X and Y. But if you're outside, it's just indication that you're in the single phase gas if it's bigger than 1, or single phase liquid if it's less than 0. So that's the idea behind the negative flash. It also makes sense because this changes between asymptotes of V, between something negative and positive, it's equivalent to changes in composition between 0 and 1. Because if you substitute your composition here, then you will see that it's only can be, so just based on this relation, if you substitute Z equal to 1 or Z equal to 0, it will be exactly boundary of your physical space, right? Because composition couldn't be negative or bigger than 1. So, and that corresponds to these two asymptotes in the negative flash. Okay, what is timing? Yeah, we don't have too much time to pass through the two-phase flash this time. I will do it next, maybe in the beginning. But the main idea in the two-phase flash is you can still solve it. It's not k-value anymore. Instead of the k-value relation, in the general negative flash, it replaced by fugacity or equality of the chemical equilibrium that is equivalent. You either say my fugacity in the liquid and vapor phase are equal to each other, or chemical equilibrium in liquid and vapor phase for each component it's equal. So this is the only difference that is comparing to the previous case when you have K value as a function of pressure and temperature. And we will take a look next time on it. Any question? It's a bit too much information, right? Yeah, but the idea is very simple. Returning back here, you have all kind of geometrical rules to define yourself. The logical rule would be can depend on evaluation of dew and bubble point pressure, or you can do the same trick with the dew and bubble point temperature by fixed pressure. And then compare where is your pressure for the given composition. You can do it for two components. It can be done for any number of the components. It's the same. You cannot just plot it here, but it's the same rules. If you're fixing composition, this let you know, so these 2 points up and down let you know what's going on. And this is for the fixed composition when you're changing pressure. At the same time, you can fix pressure and change composition. And then you will be moving between these points. And it's the same rules. If you here, in case of the negative flash, you will be, your vapor fraction will be less than 0. That indication you're in the single phase liquid. If you're here, you're in the single phase vapor. If you're in between, you're in the 2 phase. Now, when you're between, you need to compute tie line. And this is the main idea, right? So geometrically, it's very straightforward. Numerically, if you just take this assumption of the K value as a function of pressure and temperature, it's also straightforward, not so complicated, right? At least you already seen how to do it for simple K value, and with Xiaoming next time, I think not today, you will look into some of these computations of the flash and stability test. That's it. So if no more questions, then good luck with the practicals. And we have another lecture next week that will be last lecture on this thermodynamics. And then after the break, there will be 2 lectures with Maren, practicals, with Maren Brenner on the chemistry. And as usual, if you have any questions or something is not clear, don't hesitate to ask. Okay?
Okay.
Thanks, Dennis.
Thanks.
Thank you. Thanks. Bye.
Bye-bye.